Good afternoon. My name's Tim Dwyer. I'm Visiting Professor in Building Services Systems at UCL and Technical Editor of City Journal. And I'm really pleased to join you, together with many others from around the world, for this City Journal webinar on Uninterrupted Power Interpreted. Electricity powers modern living, healthcare, safety, transport, communication, commerce, industry and entertainment. Indeed, life itself can be compromised through the absence of electrical power. More than ever, the commercial world is dependent on maintaining a reliable and good quality power supply. In the UK, each office worker will effectively consume around 3,500 kilowatt hours of electricity each year. However, the loss of access to just part of a kilowatt hour of good quality power could be far more costly than the annual salary of that worker. Employing appropriate uninterruptible power supplies can mitigate risks, but as with all electrical and electronic technologies, UPS techniques are swiftly evolving. Today's webinar, presented by Kohler Uninterruptible Power for CIBSE Journal, will highlight the challenges and discuss the ways to provide resilience against power interruptions to ensure high quality continuous power whilst minimising the impact on the building's utilisation. Our presenter today, Alex Ems, is Operations Director for Kohler Uninterruptible Power and has 30 years experience of a power protection business and 19 years service at Kohler. Alex started out as a field service engineer, progressing to senior engineer, supervisor, service manager, and is now the operations director. He is qualified with an HNC in electrical and electronic engineering and a CMI level 5 diploma in management and leadership. Throughout Alex's presentation today, please use the Ask a Question button on the screen to type in your questions. You can do this at any time, and the speakers and Alex will respond to those questions at the end of the webinar. A recording of the webinar will be available through the City Journal website in a few days' time. So without further ado, I'll pass across to Alex.
Hello. Thank you, Tim, for the introduction, and thank you everyone for joining us this afternoon. A little bit about what we're going to go through today. We'll just have a quick introduction about Kohler Uninterruptible Power, and we go on to sort of talk about the continuous condition power, why we need it, and about designing it for the actual modern UPS that we put in nowadays. So we'll talk about the different architectures, the topologies and availabilities that are very important when we discuss resilience of UPS. And we've also got some questions here and information that you need and will need from your UPS supplier. At the end, we'll talk about some future developments that we see happening. But as Tim said, please put in some questions along the way that you want, and we'll be answering some of those at the end of the actual webinar. So, as I said, a quick overview of ourselves. So the company was formed in 1997, and we came in the industry looking to use very, modern innovations with partners like ABB. Acquired by Kohler later on, who are a very large privately owned US company, and they incorporate a lot of other companies such as Clark Energy, STMO, Mttr, and the like. We've also got since then offices in Singapore and Ireland, which we brought all under the Kohler Uninterruptible Power name just earlier this year. So our portfolio of equipment we look at is emergency lighting in UPS, so anything for uninterrupted. So we have single and three-phase systems, all transformerless from 1 kVA up to 5 megawatts. We have BS kite-marked emergency lighting, all modular and standalone. Along with that, we have our generator offering to marry up with the UPSs, and we're very proud of our service excellence in the industry. We've got, as you see down the right-hand side of the screen, we have a lot of experience, a lot of people in the service industry, and we're very proud, and I'm very proud of our first-time fixed rate that we managed to achieve for our customers. So some of the things we need uninterruptible supplies, in areas like data centers, hospitals, governments, manufacturing, for all sorts of different mission-critical applications, from 999 call handling, for operating theatres, for point of sale in particularly. Okay, so why is it continuous condition power important in modern buildings? Nowadays, we have IT is using a lot more of our power in our electricity use. The percentage of that is ever increasing. We're seeing an always-on expectation from our customers with the Internet of Things. And that little picture up in the screen there is at Bicester Village, where 25% of the Chinese visitors there do not have cash or cards. They use everything by their phones to pay with WeChat and Alipay and things like that. So any small outage, brownout, a small power spike can impact their ability to pay, and obviously this costs a great deal of money. So it's very important for all of us that the conditioned power is there, keeping us all online. There's also been a big focus on emergency power for safety systems. We've seen, unfortunately, the events at Grenfell. So we're seeing a big focus on emergency power for evacuation of lifts, smoke extraction, emergency lighting and things like that. So we have a lot of uses now of conditioned power, and it is becoming ever more important as we go on. So if we look at some of the very, very top level approaches to having conditioned power, if we just want to make sure the power is free of spikes and things like that, we have surge protectors. Obviously very simple, very low cost, but can't protect against brownouts and outages. Next one would be the backup diesel generators. Now these are very good for long outages, but the startup time means that power isn't instantly available. So these are often used with a UPS. And in normal time, they won't condition the power. It's only when they're online are they giving conditioned power. Another top level approach is the diesel rotary UPS, often called DRUPs. And these are an older technology, and these are typically used on large power systems greater than a megawatt. But they've been declining, and they're only about 5% of the installations at that size that use the DRUPs. And these are flywheel sets that bridge the generator startup time. And these are bulky, heavy, and relatively expensive. The most common form of conditioning is to use a static online UPS coupled with its batteries. And these provide typically short-term protection against power loss and always online, giving high-quality power conditioning. But there is some needs that we have to accommodate with static UPSs, and we go into some of that with temperatures and access for when we install these into the buildings. One of the things we look at quite critical, and we bring this into this webinar, is designing the buildings for the batteries. Now, unfortunately, this gets forgotten quite often and overlooked to some extent, but the batteries are large. The example here of in a London police station was a 128 kilowatt battery for 30 minutes, and it was large, and it weighs 10 tons. So these types of things have to be considered when we're designing buildings and the installations. Temperature control is another very important consideration for the batteries and for the UPS to some extent. A typical battery, the VRLA, which is the lead-acid valve-regulated batteries, have a recommended temperature of 20 degrees. The battery will perform better at higher temperature, but their lifetime will be lower. Every 10 degrees above 20 degrees, their lifetime will halve. So it's quite critical that we keep these as close to the 20 degrees as we can. Below 20 degrees, the batteries won't age quicker, but they will not have the performance that we would have at 20 degrees. Again, another thing that we like to highlight to you is access requirements for batteries. Batteries need to be tested and maintained, typically every 6 months. So when we put them in installation, we have to consider where they are and how easy it is to maintain. We have a picture there of, leaning across batteries, which isn't good when these batteries can be 500 or 600 volts, and it could be quite lethal. So the access to those batteries also have to be considered, where they put them and how we mount them. So we can either mount them on a rack, as you see from the top picture, and this gives us good maintenance and good airflow. However, there might be a restriction that we have to make sure they're protected against people rubbing by them and touching them. So we have also the option of cabinets, but there's always compromise either way you do this. With cabinets, there can be a restriction in airflow and maintenance access, but we can overcome this to mostly with good design when we put these in. So when we look at battery considerations and how we design the battery systems itself, we have either single or a multiple battery string. Now, the single strings are typically less expensive. However, they only have one string, so the resilience can be much lower. But it's having multiple strings with redundancy and resilience in there will cost you a little bit more, but tend to be a much better solution. Another thing that we get asked about quite often in a service aspect is the design life, which compared with the actual life. All design lives are typically around 20 degrees. Now, in reality, that might not always be 20 degrees. But a typical UPS battery of having a 10-year design life would need replacing at 7 to 8 years. And once disposed of, they are recycled and should be recycled. And the good thing is they are 90% of the actual battery can be recycled. But so why do they fail at 7 to 8 years rather than the 10-year design life? Now, battery failure is the main cause of UPS failures, and batteries fail either being overcharged or undercharged. Now, overcharging causes the battery to gas, to dry out, and if left in that condition, will run into thermal runaway. Obviously, a serious condition. If they're undercharged, this causes sulfation and loss of capacity of the battery itself. So, we need to monitor these batteries so we can see if they're being over or undercharged and if they are getting weak or high impedance. So if we monitor them, we can see this happening and we can replace any weak battery early enough to prevent a failure when it's actually needed. But to prevent over and undercharging, you can put a management systems on batteries, and this will prevent that over and undercharging, and it can, in some cases, extend that service life by up to 30%. But the main thing is it makes a much more reliable, resilient battery solution for you. So going on to the actual UPS itself and looking at components of a modern UPS, we have in front of us here a diagram, a typical UPS diagram, where we have a main supply here on the left, feeding into the booster rectifier at the bottom, into the DC bus. So that converts the AC mains into DC, which is one conversion. And then the inverter converts that DC back into AC, which feeds out to the critical load there on the right. Now, those two conversions is why a lot of modern UPSs are called double conversion or dual conversion. So static online double conversion UPS looks typically something like this. The line at the top, the bypass mains, feeding a static switch, or sometimes called just a bypass line or reserve line. Now that is in the event that the UPS needs to be maintained, or if there's a problem with it, or if there's an actual problem on the critical load itself, we can transfer no break onto the static switch to keep the critical load running. At the bottom there we see the batteries, and they can be connected onto the DC bus in various ways depending on the manufacturer. But what will happen was when the mains fails, the booster stops working and the batteries connect to the DC bus, supplying the inverter with power to continue with the critical load. We've seen some innovations with modern UPSs, and one of the main innovations over the last sort of 10, 20 years has been the removal of an output transformer, which was in the output, and that was used to step up the inverter voltage to feed the critical load. And with modern technology, with the rectifier booster and inverter, we've managed to get rid of that, increasing the efficiency in that line, and also making removal of a big transformer, making it much smaller and lighter. With those changes, we've also had to improve the booster rectifier, and that's had a lot of benefits because we've had to increase the power factor, and typically nowadays the input power factor is unity, very close to unity. So that's actually made the harmonics and things like that going back on the mains much less and much kinder to the supply in the building. We've also recently seen quite big changes in the inverter with much more sophisticated control of the actual inverter devices, the IGBTs. And we have now interleaved 3-level IGBT inverters, and these are pushing the actual boundaries of efficiency up to their best ever of over 97%. So all these advances have allowed us to make a reduction in the size, reducing the weight and the footprint of the actual UPS system itself into a point where we can actually put it into like a modular design. And we've seen here that we can now put these small UPSs into cabinets, which are all front access with solid connectors, making it the losses even less, making it much easier to service, and the whole thing's much smaller and neater and much more suits the modern environment. So we'll look at now the different types of architecture for UPSs, and we believe that we talk about these 3 main types of static UPS architectures. And the first one being standalone, sometimes called monolithic, and this is a single unit which has all the components inside, and it's like typically one of each component in there. And then we have a true modular UPS where all the components are replicated and all those modules are put into one frame. Somewhere in the middle of this we have a bit of a hybrid which we call semi-modular, and this is where some components are replicated, some components are shared, and it can be a single or a multi, and it depends on which way you look at it. So we look at the comparisons of these, and the standalone. Now this is initially a lower cost because it's you're buying one component of each one. Can be smaller, but if it's just one standalone UPS, it's got a low resilience. You have to right size from the start, so you have to put a UPS in that has the required power for your final load demand that you're designing around. Now, the other end of the spectrum is the true modular systems. Now, these have the highest resilience availability, typically have the shortest mean time to repair, and are scalable. So we can add and take away modules as required to increase and decrease the demands. The footprints are typically small, and because of the way they're modular, they can be very easy to install in small places. Now you see the picture in the middle is one of the systems we put into a hospital where the ability to take those modules out and reduce the size was able us to get that into a very tight, small space and still make it very serviceable in the future. But the downside, if there is one to that, is unfortunately the higher initial cost because you are paying for the multiple components and that flexibility. So we'll have a look at the semi-modular. This is worst of the best worlds. It's medium cost typically. It can be scalable depending on the type of it, and some of it can be part deployed. Part load efficiencies can be good because some of it can be scalable, and potentially some of the mean time to repair can be very good. But unfortunately, because some of the components are shared, the mean time to repair can be the same as the standalone. And it can be less resilient due to those shared common parts. So if it had a shared bypass, the resilience of that would be less. So there's things we have to look at in what we need. So, but one of the things we looked at the redundancy and resilience of these systems. So we look at the different UPS topologies that we see. So in the Uptime Institute, we have the different tier levels, tier 1 to tier 4. And you look at the chart in front of you, and we're looking at the redundancy part. So tier 1 is N, tier 2 and 3 are N plus 1, tier 4, N plus N, or 2N plus 1. So I'm going to run through what those redundancy level means. So first of all, we look at the N system. Now, an N system was, in this case, we're looking at a reference load of 300 kilowatts. So we have a single UPS feeding a single load of 300 kilowatts. As you see, there's no redundancy there. If that UPS isn't working, nothing will be. So this can be done in a couple of ways. We can have one standalone monolithic box, which is capable of supplying 300 kilowatts, or we can make that up out of modules, or smaller modules, which makes it scalable. But we can look at the advantages and disadvantages. Now, of course, an N system is going to be the most simple of designs, and it does provide a continuous protection to a single bus, and this is about as inexpensive as you're going to make it if you want power protection. However, there is no redundancy, and if you don't design it right from the beginning, it will be difficult to expand. And many people now want that redundancy. So we look at the N plus 1 system here. Now, the actual load here, the same reference load of 300 kilowatts, has now got redundancy through the second UPS. So we have redundancy on that feed to the load. And again, we can make that up out of different systems. So we can either use two standalone 300 kilowatt UPSs, or we can use smaller modules, and in this example we have 4 100 kilowatt modules. Now if any one of those modules or one of the standalone was to be offline, the other one would take the required load. In normal operations they will be sharing the load. So as you look at the two 300s, they would each run 150 kilowatt each unless one was taken offline. So what we're looking at here now, we'll add it on the screen, is the utilization. Of course, on the 300 kilowatt, we now have two of them making 600 kilowatt, giving a utilization of 50%. If we make it up out of smaller modules, so the 4 100s, we have 400 kilowatts. So we're utilizing the UPS higher at 75%. And that becomes a little bit more important as we move on. So the advantages of N plus 1 is now we have redundancy for the load. So we can maintain one of the UPSs, one of the UPSs can fail, one can be taken offline, and we still have protection to the load. It is still a relatively simple design, especially on the modular when it's got one input, one output. And again, it's probably the most inexpensive way of getting redundant system. Okay, but disadvantages are now the load is only fed from one bus. So if that actual one bus goes down, we have no protection. And again, if not designed properly from the start, can be difficult to expand. Now, modern load has now been developed with dual supplies. So many servers, many computer equipment manufacturers are building all their equipment with two supplies in there. And this is to be designed to be fed from two different sources. So if a power supply or the supply coming in is lost on one side, typically an A and a B, we can still run from the other side. So an N plus N system is what it says. We've got an N on side A and an N on side B. So we have redundancy. If one UPS was lost, the other UPS would be supplying the load. So again, different ways of doing that. We can have two standalones, each feeding each side of the load, or we can make it up out of smaller modules again, allowing expansion and ease of and flexibility. But each one in this case has got to have 300 kilowatts on each side. So advantages and disadvantages of N plus N is we now have redundancy at the load. We can lose either side completely and the load is still protected. As far as UPS design goes, it's quite simple. We just put two complete installations in. So for the UPSs, it's relatively inexpensive. Disadvantages, obviously, if that one UPS does go down on one side, there is no protection for that side. Again, not put in and design right, it can be difficult to expand. And now we have much more installation here. We have two distribution networks throughout the setup, so the installation cost will be higher due to that reason. Now, when we want to look at the ultimate redundancy and resilience and availability, we often get asked now for a 2N plus 1 system. Now, this is where we have redundancy at the UPS and we have redundancy at the load on the bus. So again, we're looking at this 300 kilowatt reference load, and we'll produce this either with standalone units. So in this case, we'd have to have two on each side. So an N plus 1 on each side of the load, which makes it the 2N plus 1, which is 1.2 megawatts, 1200 kilowatts of UPS, utilizing only 25% of it in normal running. But if we make it up out of smaller modules, we can put in less UPS, and in this situation, example, we have 800 kilowatts, utilizing 37.5%. Now, it doesn't sound much of a difference, but modern UPSs are running efficiently over 25%. At 25% below, they start to become quite inefficient. So the running costs and considerations have to be considered in these cases. So advantages now, obviously we have redundancy for the load at each bus. We can maintain any single UPS in there concurrently, and we have an extremely high availability to the load. And we'll talk about that just later. The disadvantages are, obviously, we have much more complexity in this system. And initial costs are high, obviously, because you're buying so much, but they can increase higher if we don't have that running in that efficient mode when I talked about the utilization. So the actual availability, what is that? Now, the Uptime Institute defines levels of availability for the data center tiers, and they calculate availability as MTBF over MTBF plus MTTR. Now, that is the mean time between failure and the mean time to repair. So we look at the levels in a data center, and you see a tier 1 level here has a requirement to be 99.671% available, rising to the tier 4 of 99.995% availability. Now, that doesn't seem much difference in those percentages, just a couple of points of a percent. But if you look on the right, that availability translates to a downtime of nearly 29 hours on average a year for a tier level 1, dropping quite dramatically to tier level 4 to 26 minutes. So that any small change in that percentage will make a big difference on the downtime. And we have to look at that when we're looking at the UPS part of the data center. So what we have to do is, we can obviously make the UPSs more reliable and the MTBF can be increased. However, if we address the mean time to repair, we can add the greatest difference to the availability of the system. So if we look at a standalone unit, for example, a mean time to repair on this means we get a fault call of the system. Customer gives us a call. We determine that there's something wrong with a unit, so we'll bring out a full spares kit, bring out everything we need. We get to site and we will diagnose the parts, take it to part, strip it down, replace the parts, test it, recommission it if necessary, and that can easily take 6 hours on a unit on site, on a big unit. Because sometimes these aren't that easy to fix. But if we look at a modular UPS, now again, the customer would give us a call, explain the issue, and if we believe that there was a definite problem with a module, we would bring out a complete spare module to site. And once we're on site, that will be swapped well under 30 minutes, sort of typically a 10-minute swap on a modular UPS. Now that makes a big time difference on the MTTR. And when we look at this example here, we can see an M+1 system, in this case 400 kilowatts, 1+1, that's got a typical mean time between failure of 1,250,000 hours, compared with 5 modules of 100 kilowatt, which is obviously with more modules we have a lower MTBF at 625,000 hours. However, as we've explained, the fixed time, the repair time for a standalone can be 6 hours easily. And for modular, it can be well under half an hour. So when we put that in the calculation of availability, the MTBF over the MTBF plus the MTTR, we get that availability 99.999 for standalone and 99.9999% for the modular, 6 nines. And when we calculate that in downtime, we have a 10 times availability improvement because of that MTTR. And you can see the downtime goes from 315 seconds down to 31.5 seconds for that type of UPS. So what do you need to do and what do you need to know when you're planning a UPS installation? Now, obviously, we need to know what the present load is, in watts, kilowatts, or amps. What type of load is it? Is it computer equipment? Is it surgical equipment? That type of information is very important because it can be regenerative or a safety service, and that will require certain design criteria that we need to know as well. Obviously, the present load might not be the future load. The load might go up or down, and of course, we need to plan for that during the design. And the other important autonomy is how long do you want it to run on battery on a mains outage. You then decide how critical is this. So what topology do you require? Is it N+1 or N+N to N+1 to keep this resilience that you require? You also have to say how much space you have available for the batteries in UPS. These can be put in separate places. Where's the battery going to be located? Because this will drive how we're going to install it. Are we going to put it in a cabinet or are we going to put it on a rack? And if the unit is remote, many people and most people now will have a communication with the UPS, either connected to their BMS or have it emailing an issue through network cards, and it can even be remote monitored by your supplier. And how, depending on where you put it, installation access may well be a consideration. And again, modular systems that can be broken down can be make that situation much easier. So some of the things you might want to be asking from a UPS supplier is, what's the system efficiency of the UPS, and especially at different loads. Modern UPSs are very efficient, and typically, they have great between 50 and 100%, but below that, what are they? And we need to be careful. And how is it rated on the output power factor? Is it unity output, which gives you more power and is equal to the kVA? Or is it at 0.8, for example? The input THDI and input power factor can make a big difference on your input supply, so we should be making sure that that is good and suits your needs. And again, the overload and short circuit capabilities of the output, the inverter, how good is it, and does it do what you require in the event of those situations? If you're limited space, you may well be very concerned about the footprint and the dimensions, and it is very important that we consider the service access. I spoke earlier on about this. We often get asked to put in a small space, but we can't service it once it's been done. So that's very critical when planning. The weight, the UPS in batteries, especially the batteries, can be extremely heavy, as we explained. So that would be a question to ask when you're planning your installation. Now, cooling requirements. The modern UPSs are much more efficient nowadays and need less cooling, but it must be considered. There are specifications, sort of typically 40 degrees max for the UPS, but the cooling requirement for the battery is probably more critical. And as explained for lead acid, we need to keep it around the 20 degrees. So once you put that system in, and we're thinking about looking after the system, which is a good thing, do we want to have a monitoring or management system on that battery? Because this should be considered. And then the actual UPS supplier, what are their service capabilities? How many engineers? What is their coverage in the UK? Do they subcontract or use direct factory trained engineers? And where are their suppliers' spares kept and held? There's no point having a 6-hour response if the spares aren't in the country to start with. So we carry on now on to what we see as some of the future developments. We see efficiency as one of the areas where people are concentrating on. So we're looking at smart deployment of the energy use, and that can be either with the modular or with what we call extra VFI, only allowing the required modules to run when required. We always get asked for an ever smaller UPS, so we're seeing smaller and smaller UPSs bringing in. We also believe we're looking at more battery management and monitoring on the VRLA, the lead acid battery. It's a relatively modern thing to be putting on batteries in the last sort of few years, and we're seeing that that's increasing the reliability and resilience of the battery itself. But talking about batteries, obviously a lot of people hear about the lithium batteries. The prices have fallen quite dramatically over the years recently, but they are still typically for UPS situations 2 to 3 times the cost of a typical lead acid, and we're not seeing that dropping, to half that in the next 10 years or so. There are limited uses of lithium, especially they are very light. So in some situations, a lithium technology can definitely be an answer, especially around short autonomies where that lithium has some advantages. But we see a lot of cyclic use now on batteries, not so much on UPS, but there's a lot of talk about it. And we see alternatives to lithium with different types of lead batteries with different chemistries such as lead carbon. And again, another trend going forward is energy storage systems. Now there's an ongoing look at, do we use UPSs for supplying some of that energy storage? We use the UPS to condition it back through, or do we use completely separate systems? But with the grid being dependent on energy storage, I think the UPS is going to be extremely critical in keeping it smooth. So That actually brings us to the end of the presentation today, and we'd now like to open this up to any questions we have. I personally haven't been keeping an eye on any questions because I've been talking, so it's over to Tim.
Well, just as well we have, and thanks, Alex. That was fantastic. Loads of information to take in there, and results. We've got lots of questions to put to you. What we'll do is we'll take the questions as we can today. Any questions we don't answer will be picked up afterwards by Kohler, and then everybody to review the whole webinar again. It will be up on the CIBSE Journal website in a few days' time. So let's pitch straight into our first question, Alex, if you're ready for it.
Yeah.
Those state, this one's actually from Vicky, and Vicky asks, those state 20 degrees C as a target for battery location. Practically, how many people actually achieve that?
Good question. We see a variety, to be honest. We always advise people to keep this at 20. A lot of the time we see around sort of 20 to 22, but some of the big problem we see is people say it's 20 degrees in my comms room, but the temperatures in the actual room can vary. So we see it might be 20 degrees at the floor, but by the time it gets to the top of the battery, it's 25. So airflow around the battery is very important, because that 25 degrees is taking years off your battery. Okay, so there's a good reason to maintain a proper space for these batteries and proper ventilation. Definitely. Well, that moves nicely into our second question. This one's from Vidya, and Vidya asks, what is the exact life expectancy of these lead-acid batteries, and after they're completed in their use as a UPS, have they got a use elsewhere? Okay, lead acids, you can buy various types. As always, you get what you pay for. So lead acid batteries come in 5-year, 10-year, 12-year, 15-year, 20-year batteries. The typical battery used in UPS is a 10-year battery, and we typically, like I said, expect to last, when kept in good condition, 7 to 8 years. At that point, they are effectively scrap, and they go for recycling. We do obviously have to, especially in this country, actually recycle everything, and that, like I said, 98% recyclable for a lead acid is pretty good. Okay, so not directly used, but certainly got an indirect use after life. Okay. Definitely, yeah. And just to follow on from Vidya there, is there any risk of these lead acid batteries catching fire if a temperature does rise too high in the space? Yeah, there is a small risk. If they're being overcharged, especially, so the UPS should be equipped with some form of temperature compensation. When the battery is warmer, we should reduce the charge voltage. It won't stop the battery getting damaged in the long term, but we can prevent to some extent the risk of thermal runaway. But if you're not treating the battery right, it can be a problem. Okay, thank you for that. Associated with the kit that is at the heart of the UPS, got a question here from Andrew, who asks, how critical is the replacement of capacitors in prolonging the life of a UPS? Yeah, very critical. Along with the batteries, capacitors and sometimes the fans are consumable items. The manufacturer will dictate when they should be changed. Failure to change those capacitors will mean that they could well fail in a quite catastrophic way sometimes. So you're putting the load at risk if you don't follow those manufacturer's instructions. Okay, one more question on the batteries. We'll move on to other areas. Is there any guidance for those heat emissions from the UPS?
And does that affect? Is that related to ratings? Or is it purely down to manufacturer's data? Does it have to be done case by case?
It's purely case by case. Obviously, a different UPS of a different size of a different manufacturer will put different heat output from somebody else's of a different size. So, a 10 kVA UPS compared with obviously a 500 kVA will have a completely different heat output. But the manufacturer's specification should clearly state the heat output from the UPS.
Great, thank you. And just a trailing question there, and I think you've answered this in your presentation, but I've been asked again about the use of lithium. Well, obviously, they're really popular, and I've got one sitting beside me here, which is my UPS for my computer. Why? Can you just reiterate why lithium batteries are not used in place of lead acid? Although I think there are occasions where you suggest they might be.
It's possible. We're all supplying lithium batteries. At the moment, it's still early days. We have very limited capacity range, as in to say we haven't got a selection of different capacities. So it only suits certain situations. Now, lithiums are definitely lighter than lead acid. So if there's a space and weight consideration, lithiums may be the option. But the cost is prohibitive still when it's not actually required, because if there's no really need for it, it will be more cost advantage in the long run for the actual lead acid. And obviously, the one thing that we don't talk about very often with lithium is the recycling of them as well at the moment. So there's an environmental impact with lithium that isn't yet sorted out. I mean, it's getting there, but at the moment when lithium is taken out, there's only a couple of places in Europe that will recycle it.
Okay, thank you very much. Okay, let's go into a couple of other areas that you've spoken about today. The questions are still coming in, and if anybody's got any further questions, please do post them. I can't imagine we're going to get through all these, but please do post them, and they will be picked up after the event if we don't take them online today. Okay, it's an interesting question. One of the later slides you were talking about Mttr, and Alan asks, is Mttr reduced if the customer has the spare kit on site? I mean, in theory, yes. It depends how good and how quick the supplier can get the spares into the country. If the supplier has the spares on hand, it'd be the same time to get the engineer there anyway. So, yeah, if you know the spares are available from your supplier, there should be no benefit. Okay, yeah, I mean, I think I recall on that slide you were showing, a large proportion of that time, of 4 hours, I think it was actually getting from the call centre from the repair centre to the site, really. Yeah, I mean, that's the point. I mean, we can, especially with modular, we can hot swap it. So, when we get a call with a modular system, we determine it's a module or not, and we take it with us. And then we take the problem off site, so that mean time to repair is very quick. If it's a standalone unit, we have to obviously get to site and then determine what the problem is, and then take it apart and fix it. Okay. Interesting question here. This one's from Dennis. And Dennis asks about the availability. One of your slides, the availability slides, you were talking about modular systems providing higher availability. But he asked, well, surely if you have more modules, you're going to have more failure, more opportunity for failure. Yeah, absolutely. As seen in the slide, the MTBF of more systems, more modules you put in reduces. But however, the almost
guaranteed repair in a very, very short time, when put into the calculation, makes the availability much better.
Which is, of course, what you're looking for.
Yeah.
Okay, thanks. Okay, I've got a query here, and this is from Jubin, and Jubin asks, is the preferred measure using input transformer or output transformer? What is the preference for best performance?
I'm guessing this customer is talking about having galvanic isolation transformers, which is a transformer used to create a new source, a new neutral reference source. And is it best to be on the input or output? It can be either. It depends on the situation. It can depend on the type of UPS, if it's dual or single input. So that is actually the best kind of question to be asking directly at the sales point and discussing with your supplier, because it depends on different situations.
Okay, thank you for that. A question from Carl here. How critical is battery conditioning when commissioning a UPS? And perhaps I can also add a question on from Yuck, who's asking from Hong Kong. What's the purpose of the maintenance process? What does that do for the battery life?
At commissioning, the batteries typically come out of the manufacturers sort of 90% charged or so. However, they need to be on charge for sort of like 5 to 7 days before you do anything to allow them to equalize out. We can and sometimes get asked to do a load test on those batteries, and that is purely to prove the calculation that the battery and everything supplied is as designed. It's not a necessary thing for the battery. The batteries have already been tested at the manufacturers, so that's not required. As far as 6-month maintenance is concerned, it's more about ensuring that battery is going to work when you need it. Batteries can be the most unreliable part of a UPS system, so as part of that maintenance, we should be checking all those batteries. So yeah, you want to know that they're going to work when required. Now, if the customer has his own monitoring system connected, they can do that very simply themselves, and it will automatically do that during automatic battery tests of the UPS if they need it to.
Okay, enough. Yuck's asked a number of questions, but one of the other queries he asked, is the external bypass required for maintenance purposes?
If you ask me as like an engineer, I always recommend an external manual bypass. You never know when you're going to need it, and it is a definite, in my opinion, a definite requirement, especially when the UPS gets to end of life. You can keep everything maintained while you replace it. As far as maintenance goes, with anything, it's good to regularly exercise the manual bypass, the breakers, and the UPS. Is it absolutely necessary to go to maintenance bypass? It's not absolutely necessary, providing you have a redundant system. But it is very important that we carry out maintenance and regularly exercise the UPS and its surrounding parts. Unfortunately, we see a lot of customers saying, don't touch anything. Just come and have a look. Though, maintenance is extremely important, and to make sure we know that system's going to work, we should do it. My colleagues sort of looking. We've got a situation at the moment where we're having trouble in a hospital. We can't change the UPS without a shutdown because they haven't got a maintenance bypass. So, although it's not essential, it's a good option.
Okay, thank you for that. A question here: is in in the modular systems, is there an inter-module physical barrier protection between the different modules in case of catastrophic failure of one of the modules?
Yeah, I mean, in a true modular UPS, each module is its own case. It's a whole UPS, and it's in its own case. And it is the fact that it is in its own metal case. So I suppose that's the answer to that question is yes.
Okay, simple answer. Thank you. A question here. This is looking at, I think it's concerning demand side response. It refers to DSR, so I presume that's demand side response.
Okay.
Is it feasible to consider UPS as battery storage for demand side response schemes at this stage? That's from Tarek in Leeds.
Yes, it is possible, and we've talked about this, but we have to make sure that we know what we're doing. The battery has to be a different type of battery. A typical UPS battery is a standby battery, not a cyclic battery. So we'd have to take that into consideration if someone wanted that. But demand side response can be done with any UPS. When you need to run off the storage battery, you disconnect the input supply and let it run. Yeah.
Okay, thank you very much. There's some technical questions coming in. We've got a whole raft of questions here. It's a fairly technical question. What's the general performance abilities with regard to step loads applied to UPS? And are there any requirements regarding interfacing of standby generators and UPS units? So we've got
two questions in that. Okay. Step load on UPSs can be 100%, no problem. And that can be single phase on one, on unbalanced single step of 100%. I can't talk for all manufacturers, but many will actually do 150% load step with no issue, which is a little bit different to the standby generators. Modern generators, providing we have modern generators with electronic governors, it does depend on the type and make of generator compared with the type and make of UPS. But, so that is really a question to the actual individual manufacturer. But typically, generator interfacing with UPSs is much better now than it was 10, 20 years ago, due to the advances on the rectifiers of the UPSs. They're much kinder to generators nowadays.
Okay, thank you very much. A question here from Jubin again. He asks, he's from the Middle East, and he's asking, in an N+1 or an N+N configuration, what's the best way of utilising batteries to avoid battery life wastage?
I see he's talking about common battery banks.
Yes, sorry.
Personally, if you've gone to the extent of doing N+1 or N+N on your UPS, I would recommend separate batteries. The batteries are one of the most, like I said before, one of the most unreliable parts. So why would you want to use a common battery to feed both UPSs? I understand, yes, if your UPS was off, that you would have that common battery available for both UPSs, but we're trying to increase resilience.
Okay, thank you for that, Alex. We're just about coming out of time here. I just see if I can select one more question that you can quickly answer. Maybe is one from Huzaifa, and Huzaifa asks: is there any risk of dangerous gases building up from recharging VRLA batteries in large installations?
The simple answer is yes, but the amount of gas depends on how the batteries performing. There will be, from a VRLA battery, there is a small leakage of gas in normal operation that has to be allowed for. But when it comes to being, if there's a fault on the battery, yes, it will output hydrogen gas that has to be considered.
Thank you very much, Alex. That was a fantastic performance. I can't remember when we got through so many questions. Well done, thank you. That was a really interesting webinar, and there's much to think about there. So, Alex, thank you very much for being such a clear and informative speaker.
Thank you.
Just to remind listeners and viewers that you will be able to review this again. Recording of a webinar with full audio and slides will be available through the City Journal website in a few days' time. So thank you all for attending. We've had loads of people online today. It's been great. And I really thank Alex for a great informative presentation. We look forward to joining you again next City Journal webinar, which is just a few months away. And with that, I wish you goodbye from London. Goodbye.
Goodbye. Thank you.